high voltage direct current, HVDC, transmission systems have become critical infrastructure in modern power grids, enabling efficient long-distance power transmission and interconnection between asynchronous AC systems. Among the various HVDC technologies, Line-Commutated Converter, LCC, HVDC systems using thyristor valves remain widely deployed for bulk power transmission due to their efficiency and cost-effectiveness. However, LCC HVDC systems are susceptible to a specific operational challenge known as commutation failure, CF, which can significantly impact system reliability and stability. Commutation failure occurs when a thyristor valve that should turn off continues conducting because the current fails to transfer to the next valve in the firing sequence. This phenomenon is particularly critical for system operators working with HVDC interconnections, as it can lead to power transfer interruptions, equipment stress, and in severe cases, cascading failures. Understanding the fundamentals of commutation, the causes and impacts of CF, and implementing appropriate mitigation strategies is essential for ensuring reliable operation of HVDC facilities. Fundamentals and causes of commutation failure. In LCC HVDC systems, commutation refers to the process of current transfer from one valve to the next using the AC system voltage. This process, known as natural commutation, requires each valve to turn on at the commanded firing angle, alpha, and turn off naturally when the current transfers to the next valve during the overlap interval, mu. Successful commutation depends on three critical factors: sufficient AC voltage magnitude, correct phase relationship, and adequate extinction angle, gamma, margin. Commutation failure occurs when the extinction angle approaches zero, gamma zero, meaning the valve does not regain forward blocking capability. The primary cause of commutation failure is AC voltage disturbance, particularly at the inverter station. Common triggering events include single line-to-ground, SLG, faults, line-to-line, LL, faults, three-phase faults, severe voltage dips, or phase angle jumps. These disturbances reduce the commutating voltage, increase the overlap angle mu, and eliminate the extinction margin gamma. Secondary contributing factors that increase CF risk include weak AC systems with low short-circuit ratio, SCR, high DC current orders, inaccurate firing angle control, harmonic distortion, improper transformer tap settings, and multi-in-feed HVDC interactions, MIDC. System operators must be particularly vigilant when operating HVDC facilities in weak AC networks or in multi-in-feed configurations where multiple HVDC links terminate in the same region. Impacts and risks of commutation failure. The physical effects of commutation failure are significant and can be observed on both the DC and AC sides of the system. During CF, two valves in the same bridge arm conduct simultaneously, creating a short circuit on the AC side of the converter. This results in a sharp rise in DC current, often exceeding 2 to 3 per unit, collapse or reversal of DC voltage, and temporary interruption of power transfer. On the DC side, these effects cause stress on valves, smoothing reactors, and transformers, potentially leading to valve misfiring or thermal damage. On the AC side, CF results in loss of active power transfer, reactive power imbalance, and voltage instability. At the system level, repeated commutation failures pose serious risks including HVDC blocking, power oscillations, loss of synchronism between grid areas, and in severe cases, blackout scenarios in interconnected grids. The recovery time following a CF event can be significant, especially in weak grids or multi-in-feed configurations. For system operators, these impacts translate to operational challenges, increased maintenance requirements, and potential reliability concerns. Understanding these risks is crucial for developing appropriate operational procedures and mitigation strategies to minimize the likelihood and impact of CF events. Assessment methods and mitigation strategies. Assessing the risk of commutation failure in HVDC systems involves both simulation-based and analytical methods. Electromagnetic transient, EMT, Simulation with detailed thyristor level modeling provides highly accurate results but is computationally intensive and unsuitable for large-scale planning studies. Analytical methods using indicators such as maximum permissible AC voltage dip, extinction angle margin, and critical fault clearing time, CFCT, are more suitable for screening studies, sensitivity analysis, and planning of protection and controls. Mitigation of commutation failure typically involves a multi-layered approach encompassing four major categories: protection and control optimization, auxiliary equipment installation, DC power coordination, and converter structure modification. Key control measures include extinction angle control, EAC, gamma minimum control, current order reduction during faults, fast fault detection and recovery logic, and advanced firing angle during voltage dips. Advanced approaches such as adaptive control based on AC voltage phase, model predictive control, MPC, and AI-based CF prediction are emerging research areas. Auxiliary equipment such as static VAR compensators, SVCs, StatComs, synchronous condensers, and dynamic braking resistors can support AC voltage, improve SCR, and increase commutation margin. DC power coordination strategies include coordinated power reduction during AC faults, power runback schemes, multi-terminal and multi-in-feed coordination, and emergency power shedding strategies. Converter structure modifications may involve series-connected converters, improved transformer design, enhanced valve cooling and ratings, or transition to voltage source converter, VSC, HVDC where feasible. Notably, VSC HVDC does not experience commutation failure since it does not rely on AC voltage for commutation. Real-world examples and operator recommendations. Commutation failure events have been documented globally, particularly in regions with weak AC systems, high-power LCC HVDC links, and multi-in-feed environments. Well-documented CF events have occurred in India's multi-in-feed HVDC systems, China's UHVDC inverter stations, Nordic interconnections, and parts of Europe with weak receiving grids. These events have provided valuable lessons, highlighting that AC grid strength is the single most important factor in preventing CF. Dynamic reactive support is essential, multi-in-feed interaction must be studied carefully, and operator training and fast protection coordination matter significantly. For system operators working with HVDC facilities, several practical recommendations emerge from the technical understanding of commutation failure. First, continuous monitoring of extinction angle and AC voltage conditions at inverter stations is essential for early detection of potential CF conditions. Second, implementing appropriate control strategies such as current order reduction during AC voltage dips can significantly reduce CF risk. Third, ensuring adequate dynamic reactive support through SVCs, StatComs, or synchronous condensers can strengthen the AC system and improve commutation margin. Fourth, developing coordinated operational procedures for multi-in-feed HVDC systems can prevent cascading CF events. Finally, considering the transition to VSC HVDC for new projects in weak grids or critical applications can eliminate CF entirely, though this must be balanced against economic considerations. As HVDC interconnections continue to expand globally, system operators must maintain a comprehensive understanding of commutation failure phenomena and implement appropriate mitigation strategies to ensure reliable and stable operation of these critical transmission assets. Commutation failure mitigation in LCC HVDC systems. Commutation failure in line-commutated converter high-voltage direct current, LCC HVDC, systems represents a critical operational challenge that can lead to power interruptions and equipment damage. This phenomenon occurs when current fails to transfer from one thyristor valve to another during the commutation process, typically triggered by AC system faults that cause voltage disturbances. The consequences include sudden increases in DC current, equipment stress, and temporary interruption of transmitted power, which can propagate instability to connected AC systems. Mitigating commutation failure requires a comprehensive approach combining system strengthening, advanced control strategies, operational optimization, coordinated protection, and robust design practices. Strengthening the AC system constitutes the first line of defense against commutation failure. By improving short-circuit capacity through the installation of synchronous condensers, static VAR compensators, SVCs, or static synchronous compensators, STATCOMs, utilities can maintain adequate commutating voltage during fault conditions. Synchronous condensers provide inherent system inertia and short-circuit strength, while SVCs and STATCOMs offer dynamic reactive power support. STATCOMs, in particular, demonstrate superior performance compared to SVCs due to their faster response times and ability to provide continuous reactive power control in both directions. These devices enhance voltage stiffness and support recovery from commutation failures, making them especially valuable in weak AC grid applications where the risk of commutation failure is highest. Enhancing converter control and protection systems represents another critical mitigation strategy. Extinction angle control, which maintains the time interval between thyristor turnoff and reverse voltage application above a minimum threshold, typically 8 to 15 degrees, forms the foundation of this approach. Constant extinction angle, CEA, control dynamically adjusts the firing angle to preserve commutation margins during system disturbances. Complementary to this, fast current order reduction mechanisms like voltage-dependent current order limiter, VDCOL, automatically reduce DC current during low voltage conditions, preventing the extinction angle from falling below critical values. Advanced fault detection algorithms further enhance system reliability by identifying patterns that typically precede commutation failures, enabling preemptive action. The integration of these control strategies requires careful coordination between rectifier and inverter stations, with modern implementations increasingly incorporating predictive algorithms that anticipate commutation challenges based on real-time grid conditions. Optimizing operating conditions provides another avenue for commutation failure mitigation. Proper transformer tap settings ensure appropriate converter valve side voltages, maintaining firing angles within optimal ranges and preventing over or undermodulation. Accurate firing angle control, implemented through individual phase control (IPC) or equidistant pulse control (EPC), ensures proper commutation sequences and preserves commutation margins. During weak grid conditions, limiting DC current reduces stress on converter valves and enhances system stability. These operational adjustments must be carefully coordinated with system loading conditions to balance power transfer requirements with commutation reliability. Coordinating AC and DC system protection schemes is essential for preventing cascading commutation failures. Fast fault clearing on the AC side minimizes voltage depression duration and prevents propagation of disturbances. In multi-and-feed HVDC systems, coordinated power runback schemes systematically reduce power transmission during disturbances, preventing overloading of healthy converters. Special attention must be paid to systems characterized by strong DC and weak AC configurations, where the electrical distance between HVDC landings significantly impacts system behavior. The China Southern Power Grid's approach to AC-DC protection coordination, which optimized 5 DC protection functions and validated them through extensive simulation testing, demonstrates the effectiveness of coordinated protection strategies. Finally, applying robust design and maintenance practices ensures long-term reliability of commutation behavior. Correct valve rating with appropriate safety margins for transient conditions prevents equipment damage during commutation failures. Insulation coordination protects against switching surges that could trigger commutation issues. Effective harmonic filtering on both AC and DC sides minimizes harmonic interaction with the AC system, which can otherwise contribute to commutation problems. Regular testing of converter components and control systems, combined with continuous performance monitoring, enables early detection of potential issues. Operator training on HVDC system operation and maintenance ensures proper response to commutation events, while effective communication networks between AC and DC systems facilitate coordinated action during disturbances. The most effective approach to commutation failure mitigation integrates all these strategies in a coordinated framework tailored to specific system characteristics and operating conditions. As HVDC systems continue to expand and interconnect with increasingly complex AC networks, the importance of comprehensive commutation failure mitigation strategies will only grow, ensuring reliable power transmission across increasingly interconnected power systems.